Good morning. Myself Dr. Shaila Dilkar Apte. This video is for discrete time Fourier transform, what we call it as DTFT. So here we go. Firstly, we'll try to understand Fourier transform of band limited aperiodic DT signals. So how the DT signals are, they are discrete in time, means time axis is digitized. So there are some samples of the discrete time signal. Now this particular DT signal can be periodic, it can also be a periodic signal. If the signal is aperiodic, its energy will be band limited, and because its energy is band limited, it can be easily sampled with sampling frequency greater than or equal to twice the bandwidth. So here we get what is called as discrete time signal. So for such aperiodic band limited aperiodic DT signals, we will see how to find the Fourier transform. It is the Fourier transform of discrete time signal, hence it is named as DTFT, discrete time Fourier transform. But if you consider the output of the Fourier transform or the nature of the Fourier transform, this Fourier transform is continuous. So this is the formula for Fourier transform. In this case, it is a discrete time signal, so instead of integration, we'll have to write summation. Summation n varying from minus infinity to infinity x of n e raised to minus j omega n. Now, if it is if there are few samples of xn, then the corresponding summation will vary from the corresponding sample, first sample to the last sample. And how to recover xn? Xn is 1 upon 2 pi integration minus infinity to infinity x j omega e raised to j omega d omega. Now, this 1 upon 2 pi is supposed to be the period of DTFT. Now we know how the sampling is to be done. So in order that the signal can be sampled, it must be band limited. And when it is band limited means when it is energy signal, I can suitably sample it with some considering the sampling frequency, which is twice the bandwidth. So in this particular process of sampling, what we do actually is we have a signal xt and it gets multiplied by the train of impulse with the spacing between the samples equal to 1 upon fs, where fs stands for the sampling frequency. So this is how it is. This is the process of sampling that is shown. This is some band limited energy signal, and what we do is we multiply it by the train of impulse. How this train of impulse is? This train of impulse is having the discrete samples with separation equal to capital T, where what is capital T? Capital T is equal to 1 upon fs, where fs is the sampling frequency. And after I multiply, I get this sampled signal. So this is what I am calling it as xn, that is the discrete time signal. Now let us move ahead. Now, in time domain, when there is multiplication, in transform domain, it will be a convolution. So, here this first graph represents the Fourier transform of some band limited signal with bandwidth of W. Now, because it is band limited with bandwidth of W, I am representing the bandwidth between minus W to plus W, and it is customary to represent it in the form of a circle. So this circle, in the form of a triangle. This triangular representation does not mean that at this point the corresponding value is maximum and at omega it depends and it will become 0. It's not like that. So this triangle does not say that the corresponding response will be triangular shape, but it is customary to represent the corresponding bandwidth spectrum of the signal with bandwidth W in the form of this triangular shape between minus W to W. So this is supposed to be the spectrum of your analog signal. Now what is the spectrum of impulse train? It is again the train of impulse, but it will be having the spacing between the two samples as fs. In the earlier case for analog signal, it was 1 upon fs. Now it will be Fs here. And when these two signals convolve, what will happen is the corresponding triangular shaped waveform will be replicated at each position of this particular impulse in the spectrum. So at minus Fs it will be replicated, at 0 it will be replicated, Fs it will be replicated, it will also be replicated at 2Fs and so on. It will also be replicated minus 2Fs, minus 3Fs and so on. So it is continuous, you can say, and it is replicated on either side from minus infinity to infinity. So this is how the convolution of the analog signal with the Fourier transform of the signal and the Fourier transform of the impulse train would look like. Now, let us see how to find the Fourier transform now. So, suppose we have the signal xn, it is equal to 1 for n varying between 0 to 3. So, there are 4 samples in the signal. At n equal to 0 it is 1, n equal to 1 it is 1, n equal to 2 it is 1, and n equal to 3 it is 1. So, there are 4 samples in the signal and equal to 0 otherwise. So, this is supposed to be a signal which is supposed to be band limited, and hence I can sample it, and after sampling I am getting only these 4 samples. Outside this it is equal to 0. Now let us find e raised to j omega x of e raised to j omega n. This is the Fourier transform of this discrete time signal. So how it is? It is summation n varying from minus infinity to infinity xn e raised to minus j omega n. Now this n varies from 0 to 3 only, because from 0 to 3 only the signal is existing, otherwise it is 0. So I put the values of summation for n equal to 0 to infinity, and if I put n equal to 0 I get the value as 1, n equal to 1, it is 1 into e raised to minus j omega n. So e raised to minus j omega plus e raised to minus 2 j omega because n is equal to 2, and plus e raised to minus 3 j omega because in this case n is equal to 3. So I get xn e raised to j omega n, I can write it as 1 plus. Now e raised to minus j omega can be written as cos omega plus j sin omega, because it is e raised to minus j, I will write cos omega minus j sin omega plus cos 2 omega minus j sin 2 omega and so on. So I get this x of j omega n expression. Now how to write the closed form expression for this? So what I will do, I will multiply this equation by e raised to minus j omega, and I will get this 1 is multiplied by e raised to minus j omega, this is multiplied by e raised to minus j omega, so it becomes e raised to minus 2 j omega. So in this fashion I get this equation 2. Now when I subtract equation 2 from equation 1, that is when I do 1 minus 2, the corresponding e raised to minus j omega, 2 j omega and 3 j omega will cancel. I will have 1 and minus e raised to minus 4 j omega on the right hand side. And left hand side it is e raised to x of e raised to j omega n into 1 minus e raised to minus j omega n. Right. So x of e raised to j omega n, I can write it as 1 minus e raised to minus 4 j omega divided by 1 minus e raised to minus j omega. This particular expression for this x of j omega n is called as closed form expression. Closed form expression, it is easy to represent. Otherwise, there will be 4 terms you will have to write. Instead of that, I can write some numerator and the denominator. So it is called as closed form expression. Now let us see how to find the magnitude and the phase response. What I can do is I can simply write a MATLAB code. I can write the corresponding equation for the response 1 plus cos omega, cos 2 omega, cos 3 omega and minus j sin omega, sin 2 omega, sin 3 omega, and then I calculate it for different values of omega. So I am writing omega equal to 0 is to 0 0.1 is to 20. So I am calculating for different values of omega. Actually, it is existing for all values of omega which are continuous values. Remember this. And similarly, I can write down the equation for the phase, and I can find out the phase response as well. Okay. This is angle x. So when I calculate angle x, I can write the corresponding phase response. So this is how the magnitude response would look like. What is the period for this? It is equal to 2 pi. Here it is written as 2, but its angular frequency is a multiple of pi. So this is 2 pi. So from 0 it varies like this, and at 2 pi it again reaches the maximum value, and between 2 pi to 4 pi it repeats itself, 4 pi to 6 pi again it repeats itself. So it is a repetitive spectrum, but it is a continuous spectrum. We have calculated it because we are using a digital computer, and we have calculated it for different values of omega 0.1, 0.2, 0.3, etc. But remember that it is a continuous spectrum. Similarly, if you calculate the phase response, it will also have period equal to 2 pi. So the phase response varies from 0, this way, this way, this way, this way, and it comes to this. Right. So the corresponding response, phase response, you will find that the phase response has one complete cycle up to this point. Again, from this 2 pi to 4 pi, it repeats itself. I hope you understand. Now let us try to find out the inverse Fourier transform of this function given to you. X of j omega is given as 1 between minus w to plus w, as we have represented for the analog signal, and it is equal to 0 otherwise. What is the period? The period is between minus pi to plus pi, so corresponding period is 2 pi. So how I recover xn? Xn is equal to 1 upon 2 pi, that is the period. Integration minus infinity to infinity x of e raised to j omega, e raised to j omega, and d omega. Why this integration from minus infinity to infinity? Because it is a continuous spectrum, so it is the integration here. So 1 upon 2 pi integration minus w to w, because the spectrum exists only between minus w to plus w. So e raised to j omega and d omega. So it is equal to 1 upon 2 pi nj e raised to j omega n minus e raised to minus j omega n. So if I just put the values, I get sine omega n upon n pi. So I can write sine omega n upon omega n into omega by pi. So I am multiplying and dividing by w. So I get this as a sinc function. Right. Now, this particular value will tend to omega upon pi, because sine omega n upon omega n will tend to 1 when n tends to 0. So, at n equal to 0, it will tend to omega upon pi, and otherwise it will vary as sine omega n upon omega n. So, it will be a sinc function. Now, this particular sinc function is a discrete function. Do you follow? This is a discrete time signal. Now, what is the conclusion that we can draw from this? When the DT signal is aperiodic, the discrete time Fourier transform is continuous and is periodic in frequency with period equal to 2 pi. And when the signal is continuous and periodic in frequency domain, its inverse discrete time Fourier transform is aperiodic and discrete. So vice versa is also true. Consider the unit impulse. Let us try to find out DTFT of unit impulse. So unit impulse is also a discrete time signal. We just put the corresponding value of delta n in the formula. So x of e raised to j omega summation n varying from minus infinity to infinity delta n e raised to minus j omega n. So it will be equal to 1. So how the spectrum would look like? It's a constant value for all frequencies, but it will be periodic with period equal to 2 pi. So it's varying between minus pi to plus pi. Now let us see how to find out discrete Fourier transform of DTFT of this particular signal xn. We have used the shifting property of impulse function. We can define DTFT as a function defined by x of j omega is equal to summation k varying from minus infinity to infinity delta omega minus k2 pi. So it is representing this DTFT. So x of j omega e raised to j omega is equal to delta omega. How delta omega is? Delta omega is having the period equal to 2 pi minus pi 2 plus pi, and what is the value at omega equal to 0? It is equal to the corresponding value equal to delta omega. So what is xn? Xn is 1 upon 2 pi because 2 pi is the period. X of e raised to j omega, e raised to j omega d omega. So 1 upon 2 pi, 1 integration minus pi to plus pi because this is the period, d omega e raised to j omega and d omega. So at omega equal to 0, it is equal to 1, and when I put corresponding value as 0 over here, the corresponding value is 1. So x of n turns out to be 1 upon 2 pi. So corresponding value of this discrete time signal will have the impulse value, the corresponding value of the impulse is 1 upon 2 pi. Is that right? Now DTFT of exponential sequence. So suppose I have a sequence xn is a raised to n un with mod a less than 1. Let us consider a equal to 0.1 for example. Then e raised to j x of e raised to j omega is summation n varying from 0 to infinity a raised to n e raised to minus j omega n. Why 0 to infinity? Because it is appended by un. So n is equal to 0 to infinity, I put it inside the bracket a raised to minus j omega raised to n. So whatever is there inside this bracket will appear here. So how to write the closed form expression? 1 upon 1 minus whatever is this bracket comes here. So a e raised to minus j omega n. So magnitude part, I can write it as magnitude of this function. So if I calculate the magnitude, it is represented like this, and argument means the corresponding angle will be equal to the imaginary part divided by the real part. So this is minus arc tan of a sine omega divided by 1 minus a cos omega. So if I write the MATLAB code to represent the corresponding equations, and if I find the corresponding magnitude and phase response, it would look like this. Okay. Now find DTFT of xn. Suppose this xn is given to you, half raised to n plus 1 upon 4 raised to n un. Now how to find the discrete time Fourier transform? So e raised to j omega, this is as per the formula. So what I do, I put this particular first term, then I multiply by e raised to minus j omega, second term e raised to minus j omega. So 1 upon 2 summation n varying from 0 to infinity because it is appended by un. So what is the term here? Half e raised to minus j omega raised to n. This term can be written as 1 by 4 e raised to minus j omega raised to n. So whatever this bracket is there, no, it will appear here. Whatever this bracket is there, it will appear here in the closed form expression, same as Z transform that we have done. So if I simplify, I get this as the discrete time Fourier transform for the corresponding xn. Find inverse DTFT of e raised to j omega is equal to 3 cos of 4 omega. So I can write this 3 cos of 4 omega as 0 plus 3 by 2 into e raised to j 4 omega plus 3 by 2 e raised to minus j 4 omega. So I expanded this cos in terms of the exponential functions. So you will find that the corresponding sample at x of 0 is equal to 0, x of 4 is equal to 3 by 2, and x of minus 4 is also 3 by 2. Just comparing the corresponding coefficients, I can extract what will be the corresponding xn. The same result I can also obtain using your standard formula. So 1 upon 2 pi integration minus pi to pi because the period is 2 pi. X of e raised to j omega, e raised to j omega and d omega. So 3 upon 4 pi because this 3 is there. Then integration minus pi to pi, e raised to j 4 pi. Again I expand this cos as e raised to j 4 omega plus e raised to minus j 4 omega upon 2. So that 2 comes here and it becomes 4 pi. So 3 upon 4 pi. So I just combine these e raised to terms, and if I simplify, I will find that 3 upon 4 pi into 2 pi. This is for n equal to plus or minus 4. So it comes out to be 3 by 2 again for n is equal to plus or minus 4 and equal to 0 otherwise, because when n is equal to 0, sine of 0 divided by 0, this will tend to 1, this will also tend to 1. So there is a minus sign, but when n is equal to 0, you will have a minus sign here. So 1 minus 1, so it will give you 0 at n equal to 0. Thank you so much.